بسم الله الرحمن الرحيم ربي اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي. Uh, I welcome you all to the class of ultrasound physics and instrumentation. So, I'm Dr. Hambacha, PhD Diagnostic Ultrasound Associate Professor. So today we'll discuss about the attenuation and the effect of attenuation on different tissues, right? So first of all, you will have to go through a little bit about attenuation once again, and that will be just introduction to attenuation. So attenuation means reduction in strength of sound wave, and the strength of sound waves is actually amplitude, so reduction in amplitude of sound wave is called attenuation. As you can see, this attenuation, which is written over here, that represent the nature of sound wave. Gradually, the amplitude of sound waves is reducing as it moves away from the source. So, the attenuation coefficient of soft tissue is 0.5 decibel per centimeter per megahertz. For example, if sound wave propagate in soft tissue for a distance of 1 centimeter and the frequency is kept constant at 1 megahertz, then 0.5 decibel attenuation will occur at a distance of 1 centimeter. So the assignment, I don't know which assignment that was which you were talking about, but probably the assignment will be related to attenuation. So we'll discuss about that. But here is an example. Calculate the total attenuation. The attenuation coefficient is 3 decibel per centimeter and the depth is 8 centimeters. So sound will travel the distance of 8 centimeters. And the attenuation coefficient which is given over here plus is 3 decibel per centimeter. For example, 1 centimeter, the medium at the distance of 1 centimeter sound will be 3 decibel. Now, if the sound wave travel at a distance of 8 centimeters, how much will take help from cross multiplication equation? How you can use the equation which is given over here. Attenuation is equal to attenuation coefficient multiplied by distance. But you can apply cross multiplication equation as well. So x multiplied by 1 is equal to x and 8 multiplied by 3 is equal to 24. So we'll get a 24 decibel attenuation for distance of 8 centimeters. There's another example. You can see a sound beam is attenuated 12 decibel over a distance of 4 centimeters. So what will be the attenuation coefficient? That's again too easy. You can use the cross multiplication equation. So for the cross multiplication equation, you will have to first of all make two little equations, and these will be 12 decibel attenuation occurs at a distance of 4 centimeter. Then what will be the attenuation coefficient? By attenuation coefficient, we mean attenuation at 1 centimeter depth. So if sound wave travel at 1 centimeter, what will be the attenuation? So we don't know that attenuation, and that is called attenuation coefficient. So again, I'll remind you that attenuation coefficient means the amount of attenuation that occur at a distance of 1 centimeter, and the medium is called attenuation coefficient. So we are going to find the attenuation coefficient, so that will be cross multiplied, and here you can see x multiplied by 4 is equal to 12 multiplied by 1. So x is 4 is multiplication, and this side of the equation will bring it on the other side, and it will become 12 divided by 4. So 12 divided by 4 is equal to 3 decimal. So the attenuation coefficient will be 3 decimal. That's easy, right? Now, there is another example, but it's a little bit different, because here both the parameters, because attenuation coefficient depends upon the frequency as well as the path distance. You can say the medium. So what will be the total attenuation to 8 megahertz pulse? I mean, the frequency is 8 megahertz used over here, and the sound waves traveled for 5 centimeter in soft tissue. So if the sound wave is traveling in soft tissue, so we should know that in soft tissue the attenuation coefficient is 0.5 decibel. Here. Both the variables are changing at the same time. That's why it will become a little bit difficult for us to determine or to know about the total attenuation with the use of 8 megahertz frequency at a distance of 5 centimeters in soft tissue. So here we'll assume that the frequency is not changing, or any one variable will be kept constant. So for the time being, we are assuming that either frequency or distance is not changing. So at this time, we can say that the distance is kept constant, right? The distance is 1 centimeter. It's not changing. But if the sound wave were traveling at a frequency of 1 megahertz frequency, there was an attenuation of 0.5 decibel. We are talking only about 1 centimeter depth, right? We are assuming that distance is not changing. So how much attenuation will be there at 8 megahertz frequency? So we'll calculate with the help of cross multiplication. And again, here you can see x will be multiplied with 1, and 8 will be multiplied with 5. So 5 adds 40, and decimal point is 1 degree, so we will get a 4. So 4 decibel attenuation will occur if we are using 8 megahertz frequency at only 1 centimeter distance. But now we are assuming that the frequency is 8 megahertz, and at 8 megahertz frequency at 1 centimeter distance, 4 decibel attenuation is occurring. So how much attenuation will occur if the sound will travel for a distance of 5 centimeters? So again, we'll use cross multiplication. X will be multiplied with 1, and 5 will be multiplied with 4. 5 4s are 20, and we'll get that 20 decibel attenuation will occur if the frequency is used, frequency which is used 8 megahertz, and the sound will travel in soft tissue for 5 centimeter. So at that region, that frequency, 20 decibel attenuation will occur. So what will be the effect of attenuation on image? So you know better than me that with attenuation, sound wave main beam is reducing in strength. And just imagine this is lever, you have placed your transducer over here, the sound waves are now propagating in the medium. And you know that in the soft tissue, the sound waves are attenuating at a rate of 0.5 decibel per centimeter per megahertz, right? So if you are using 8 megahertz frequency over here, then 4 decibel attenuation will occur at distance or depth of 1 centimeter. But if you are using 4 megahertz frequency, which we are using routinely in abdominal examination, then you can say that 2 decibel attenuation will occur at 1 centimeter depth. And just imagine this: you are performing ultrasound of this lever, and the sound waves are traveling at a depth of 10 or 15 or 20 centimeter, which is the usual cardiocranial length of the lever in our population, right? I'm talking about our population. But just assume that the sound wave are traveling at a distance of 8 centimeter, just for simplicity, for the simplicity of calculation. If sound wave travel for a distance of 10 centimeter in the soft tissue, or you can say in the liver, and you are using 4 megahertz frequency, then how much attenuation will be there at a distance of 10 centimeter? How much attenuation will be there at a distance of 10 centimeter if we are using 4 megahertz frequency? So at 4 megahertz frequency, the attenuation coefficient will be 2 decibel, right? So if 2 decibel is the attenuation coefficient, by attenuation coefficient we mean that 2 decibel attenuation occur at 1 centimeter distance. So how much attenuation will be there at 10 centimeter depth? So it will become x, and we'll again use the cross multiplication equation. So x multiplied by 1 and 2 multiplied by 10, so it will become 2 multiplied by 10 become 20. So it will become 20 decibel attenuation. So do you know what is the meaning of 20 decibel attenuation? So if you reverse it, that according to the decibel equation, which we have already discussed in the last classes, by 20 decibel attenuation, we mean that if we are talking about the amplitude, sorry, if we are talking about the intensity and power, then it's mean 100 times. 100 times reduction of the sound waves will occur at 20 decibel attenuation. So by 20 decibel attenuation, we mean that the sound waves are sound waves weak at a rate of 100 times. For example, if the sound waves were near to the transducer at the proximal portion of the lever, if the sound waves were as strong as 100 times. Either you are talking about the intensity or the power. So if the sound waves are 100 times stronger, then at a distance of 10 centimeter, the sound waves will be 100 times weaker. So if they are 100 over here, then there will be 1 over here. So this is a very huge difference. This is a very great attenuation. The sound waves are weakening substantially. So what will happen? All the echoes which are returning back towards the transducer from the superficial from this region, they will be strong enough, but the echoes which are coming from the deep part of the liver, they will be too weak. So there will be a very great difference between the echoes coming from the proximal part of the liver and the deep part of the liver. So there will be a great difference in the echogenicity of the superficial and deep part of the liver. Of course, the brightness of the image and the ultrasound screen depends upon the returning amplitude or echo amplitude. If the echo amplitude is greater, the structure will appear brighter. and if the echo amplitude is weaker, then the structure will appear darker. So there will be a very great difference between the superficial and the deep part of the lever. So how will it be compensated? We are using time gain compensation for it, which is called TGC, right? TGC, depth gain compensation, DGC, or time gain compensation, TGC, will be used over here, right? So here you can see this is an ultrasound image. The transducer is over here. This is the footprint of the transducer. And it shows that the convex transducer is used over here. And now the sound waves are traveling in the lever like this. And you can see in this image, at this region, the sound waves have traveled 20 centimeter at depth, right? So if the sound wave are traveling at 20 centimeter, then the attenuation will be doubled as we have calculated. But we have calculated attenuation at a 10 centimeter depth at this region, right? So at this region, the attenuation was 100 decibel, 20 decibel, that was 100 times difference in the superficial and deep part of this image. So how will it be compensated? So we have already discussed that we'll use TGC. So it is a TGC. Some of the students will be unacquainted with the TGC. So TGC are sliding knobs on one side of the ultrasound machine. These sliding knob can be moved from right to left, left to right. So you can slide these knobs, right? But the curve of these knobs will be like this. This will be an oblique curve. So the deep part will be compensated more as compared to superficial part. This deep knob, sliding knob, represent the deep part of the image, and the superficial knob represent the superficial part of the screen. And all these other knobs are representing the intermediate part in the screen. And gradually, echoes coming from the deep part, which are taking more time. That's why it is called TGC, because all the echoes taking more time for coming back towards the transducer. They are giving more gain. They are compensated with more gain as compared to the echoes coming from the superficial part. So this the deep and superficial part of the lever will appear at the same echogenicity. And state of the art cutting edge modalities, nowadays there is artificial intelligence, and you will have a quick scan knob in the control panel of the ultrasound machine. If you once press that quick scan, so all the settings will automatically be adjusted according to the artificial intelligence, the information already received by the machine. So according to those information, the further settings of the machine will be adjusted automatically. So, but you will have to use the TGC, because that artificial intelligence work very well. But if you once activate the artificial intelligence for the enhancement of the image, then multiple other things will also be obscured. Just for example, we are interested in the shadow of highly attenuating structure, but with the help of artificial intelligence, that shadow which was created due to the highly attenuation will also be diminished. So you will have to use the artificial intelligence as well as manual setting, but I will prefer manual setting. All right. If the liver becomes fatty, so what will happen with the fatty liver, right? So in the cases of fatty liver, fat will accumulate in the hepatocyte in the form of food vacuole. The entire cell will become occupied by the food vacuole if you are taking too much fat as we are taking in our routine life, in our habits, right? We are taking and the in our daily life. Every morning we are taking halwa puri, right? So there is halwa puri means we are depositing a huge amount of fat in the hepatocytes, and once these hepatocytes are filled with the fat in the form of food vacuole, so these fat acts as scatter. And one of the mechanism of the scattering is the scatter. So if the number of scatter increases, then the attenuation will also increase, and this way the sound wave will become weak and they will enrich to the diaphragm, right? So this is the diaphragm. So according to this attenuation and this scattering mechanism, the fatty liver is divided subjectively into three grades, and these grades are mild, moderate, and severe fatty liver are steatohepatosis. As some reports you will see hepatosteatosis or steatohepatosis. These are also terms used for the fatty liver. But this mild, moderate, and severe fatty liver will become due to attenuation and the accumulation of fat in the form of food vacuole in the liver, right? So if there are a large number of fat accumulated in the liver, so there will be more attenuation in terms of scattering, and the sound wave will not reach to the diaphragm, and that will be grade 3 fatty liver or severe fatty liver. But if the fat accumulation is a little bit less, then what will happen? The sound wave will move through a little bit larger distance, but now you will see that the sound wave will reflect much more from the superficial part as compared to the deep part, and there will be a great difference between the superficial and deep part of the liver. And in contrast with the kidney, there will be a great difference in the superficial part of the liver echogenicity and the echogenicity of the renal parenchyma. And according to that difference, we can say that either the liver is grade 1 or grade 2 fatty liver, mean mild or moderate fatty liver. So you will study this fatty liver grading in the and the subject of your abdominal ultrasound, but you should know how is it occurring, right? And then what is going on with the bone, right? So you know about the bone that all the sound waves which are striking the superficial wall of the bone, which is an interface, strong interface, and between the soft tissue are here. In this case, this is an interface between the cartilage and the bone. So this become a strong interface, and almost more than 80 to 90% of the sound waves will be reflected back from this superficial strong reflector. And some of the sound waves which are entering the bone, they will be attenuated, right? So what will happen to those sound waves? They will totally be attenuated. They will totally be absorbed. So there is a huge amount of absorption in the bone. So with that absorption, the deep bone will disappear. It won't be appearing on the ultrasound machine, right? So in the case of bone, you can see only the cortical part of the bone as an echogenic line, but the deep part of the bone will not appear, right? This is black area behind this bone, and this you can term as acoustic shadow as well. But this is a huge acoustic share. That's why you can't differentiate it from other structure. But in the case of a renal stone or anything else, you can see this is a kidney. There will be a stone in it. So the surrounding tissue will have average attenuation, but the stone will have high attenuation. That's why the stone will render a posterior caustic shadows. This part will be a shadow, and that's why you can differentiate it. This is a posterior caustic shadow. So the same way, this is also a shadow because no sound waves are going to this area. No echoes are coming from that region. That's why that appear black and echoic, and this is due to absorption of the sound waves. Now here you can see this is a cystic structure, fluid filled structure, and you can see a distinct posterior acoustic enhancement. So as you already know that if this is a cystic structure and there is low attenuation in that cystic structure, but the tissues adjacent to it, this cystic structure on either side, these are soft tissue, and there's an attenuation of zero point 0.5 decibel per centimeter per megahertz in these adjacent tissues, but there is almost low or no attenuation in the cystic structure. That's why the strong sound waves are coming to this region. This region is insulated by strong sound waves, and whenever echoes are coming back from this region, although the nature of the tissues at this region and this region, they are the same, but these echoes are strong enough that appear bright as compared to the adjacent tissues. That is due to the presence of this specific low attenuating structure at this region. So low attenuating structure will have posterior acoustic enhancement, but solid structure will have posterior acoustic shadow. And here you can see what's happening with the gases. These are intestine containing food particles along with gases, and you can see these are gases. So gases are strong reflector. Much of the sound wave will be reflected from the superficial reflector and between the soft tissue. So here these are soft tissue and the air. So the interface between the soft tissue and air will be strong enough, and much more sound wave will be reflected back from that reflector, and the sound waves which are entering the air, that will be absorbed, right? Then what will happen with calcification? These are highly attenuating structure, and with the highly attenuating structure, sound waves will be absorbed in it. And according to this attenuation, the um, different tissues are classified into three distinct groups, right? And these are highly attenuating structures, average attenuating structures, and low attenuating structures. So the example of highly attenuating structures are bone, hair, scar tissue, fibrous tissue, fat, stones, and so on. And the example of average attenuating tissues are organ parenchyma. And the example of low attenuating structure is fluid filled structures. Well, here you can see this is fluid. So now our session uh, will be finished. So that's why I'm going to finish it to myself, and we are coming back to study interfaces, right?
Okay, sir.